Hi, I'm Stas, and today I want to talk about building particle system in TouchDesigner, and especially particles with some kind of complex sensory-based behavior. I will use boys as my example. It's a simple flocking algorithm, and many of you already know it. You can find several implementations around TouchDesigner community. And this video is not about boids itself. I'll use it as a good test case. The real topic is different. What choices do you have when you build any kind of particle simulation? And when should you pick one approach over another? I will show you the same flocking behavior built in different ways. So the visual result will look similar most of the time. What changes is the architecture underneath. The first choice to make is between feedback pop and the particle pop. Feedback pop gives you a loop and nothing more. It takes your data from the last frame and gives it back to you this frame. Every point is created once at the start and lives forever. The operation inside the loop do all the work. In my opinion, it fits the situation where you need a feedback loop for other purposes than particles, but you can also build a particle system inside it. It also allowed me to show you the algorithm itself in its most basic form. So, let's dive in. Two neighbor pops already did some work for us. For each particle, they look at nearby particles within a certain radius and give us the average, or an average weighted by distance, where a closer particle matters more than the farther ones. That is what I choose for my Boyd simulation. It's also possible to get all information about neighbors as an array, but that's for more advanced GLSL users, and I will not cover that option here. I will use two neighbor pops of different radii here, not three like in more classical Boyd version. One radius is for separation, and the second radius is both for alignment and cohesion. This is simpler, and it's enough to show flocking behavior. I know that some people are nervous about GLSL. That makes sense for GLSL top because thinking in pixels is a real mental shift, but GLSL pop is much simpler. Here I have the same algorithm built in two ways, one using math combined pop and another one using GLSL pop. Let me switch between them. As you can see, no difference. Same steps, same order, same result. So you can build all of this with nodes, but GLSL is a shorter way to write the same thing, and also it provides you some comments. By the way, all the shader code from this tutorial will be in the public Patreon post, so anyone can read and you can recreate all I have here. The full project file, which I'm using right now, with all the network and rendering, will be available for any paid tier. Links in the description. So let's look into the code. And the separation works like this. The particle looks the average position of all nearby particles, find the direction from it, and multiply this direction by a separation strength value. That's the separation force. Cohesion works almost the same, just reversed. So the particle looks at an average position and steers toward it instead of away from it. And alignment is different. It doesn't look at the position at all. It compares the particle current direction with the average direction of all nearby particles and steers to close this gap and be alignment with the direction. Those three forces get added together into one combined push. Now, if the particle jumps straight to this new direction, the motion would look chaotic. So instead, we need to somehow control it and blend. The particle, uh, the particle turns gradually from its current directions toward desired one. How fast it can turn is controlled by one parameter, which called the U-turn rate. At low values here means slow, smooth turning. At high values means almost instant turning, which will be more chaotic and more fish-like instead of flock and glide. And speed is a separate from direction. A cruise speed parameter decides how fast the particle moves once direction is already set. And at the end, we write the new position and velocity and passes to the next frame. And these two parameters can be different in different variations of Boyd's algorithms. I prefer use this version with separate turn and speed controls values. And one more thing before we move on, I use limit pop here to keep particles inside a certain volume. It can be done differently. Here I keep it separately in a limit, so GLSL code stays focused only on the behavior itself and not on the bounding conditions. Now let's move to the second version. Here, the second idea to remember, if you need a feedback loop specifically for the particles, but you still want to control everything yourself, use particle pop with time integration turned off. What actually changes in the code? Almost nothing. The particle already has built-in attributes like position, age, velocity, and more. I just use those built-in names instead of my own. The steering logic, the separation, alignment, cohesion, turning, and the speed stays exactly the same. So, you may ask, why bother switching it at all? Because particle pop gives you control over the birth and death. In this particular Boyd's scene, I'm not really using this control much. All the particles start together, just like in the feedback version. But that control is here and it's useful, and let me show you in a small separate example. Here, particles are born based on the audio spectrum and removed based on the texture and the mouse position. I made a separate tutorial focused only on this example, so if you want to go deeper, watch it. The point here is simple. Particle pop lets you decide not just how many particles exist, but where they appear, when they appear, and how long they stay alive, and under what condition they disappear. So, one more time, more clearly. Feedback pop is usually better for feedback loops that are not specifically about particles. And use particle pop with integration off if you want full control over the particle motion and also particle lives. Feedback pop, on the other hand, fits better when you need some information from your previous frame, but you are not calculating the particle motion. We will see it again in the final patch. Now let's talk about time integration. This is where things really change. With time integration turned on, particle pop updates position and velocity for you using a physics formula you could find in a wiki. This formula uses mass, drag, and other attributes. It needs only one thing for you, the force applied to the particle in this frame. At the start of every frame, the part force attribute resets to 0, and your job is to write a value into it. Then particle pops takes care of the rest. It recalculates the new velocity and the new position based on this force. It sounds convenient, but there is a problem. Our old algorithm doesn't fit this model anymore, since it directly sets the final velocity. And with time integration on, we cannot just set velocity directly, because it will mess up with the particle pop calculations. So here is the ugly shader I built just to explain the idea. I called it reverse calculation version. It calculates the same target direction and the same target cruise velocity as before, but instead of writing this velocity directly, it asks a different question. What force should push the particle to reach that target velocity in the exactly one integration step? To answer that, it uses delta time, basically 1 divided by your current FPS, and work backwards through the integration math. This is useful only as a learning example. I show the connection between direct velocity control and the force-based integration, but I do not recommend using this pattern in a real project. If you need the direct velocity control, just turn time integration off, like in previous version. And if you are using integration, it's better to redesign your algorithm around this particle force from the start. That's what we're gonna do. Okay, now let's build it properly. And here is another idea to remember. With time integration on, you get mass, drag, and other physical attributes that handle automatically. But you cannot just take any popular particle-based algorithm and drop it in. You need to rethink this algorithm and how it produces force. So what's I have here? The separation, alignment, and cohesion still combine into one desired heading, just like before. But now the particle asks the two separate questions instead of one. First is which way do I need to turn? It takes the desired heading, removes the part that already matched the current direction, and keeps only the sideward part, which actually can rotate it. That becomes the turn force. And second, separately, am I too slow or am I too fast? It compares its current speed to the cruise speed. Too slow, push forward, too fast, push backwards. These two forces get added together and written into a part force attribute. And particle pop does the rest. Because this is now a real force, the particle mass actually matters. The heavier particle responds more slowly to the same push. You could also use drag and velocity damping here, and it will influence your simulation without without need to write any extra code for this. So the trade-off is clear. With time integration, you get the proper physical behavior and a lot of settings for free. And you don't need to write extra code for this. But you cannot just reuse any existing algorithm unchanged. You need to adapt it and to think in terms of particle force in one particular frame. So far, every version has used the same way of sensing the world, neighbor pop, which check in nearby particles directly. And there is two problems with neighbor pop. First problem is the cost. The more particles you have, the more expensive neighbor pop becomes, even with the same max neighbor setting. Here on my setup, when I switch from 5000 to 75,000 particles, neighbor pop becomes too slow, especially when the particles clump together. And the second problem is representativeness. Neighbor pop has a maximal neighbor count that you can set yourself. And the lower this value is, the less GPU time it takes to cook. But if the real number of nearby particles is much higher than this value, then neighbor pop will only samples the limited subset. And the average position and the average velocity it gives to you may no longer represent the real neighborhoods. And in dynamic particle simulation, this can show up as a glitches, sudden burst, or repeating unstable patterns. Let me try to show you in a slightly exaggerated way, so you can see it more clearly. I will change only this parameter and look how it affects the results. So, neighbor pop gives you accurate per particle local information, but that accuracy has a real and growing cost, and it can misbehave when you hit this limit. This is where the probe grid comes in, and honestly, this might be my favorite way to build particle behavior right now. The core idea is this. Instead of particles searching for other particles and gathering information from them, we placed a fixed grid of the probes or the sensors around across the space. Now the neighbor pop provides each grid point with information about nearby particles. These limited grid points store the information, and later particles can read it and use it in their algorithm. This changes two things. First, you need to rethink your algorithm again. It can no longer rely on direct per particle neighbor data. And second, and this is a big benefit, you can use far more particles. Let me show you. And the 50,000 particles, it's still running smoothly, and only I need to change some values of my uniforms so this simulation works better with such amount of particles. If I push even higher, I start to see some slowdown around 200 particles, 200,000 particles or something like this. At that point, rendering the geometry becomes the main bottleneck. I could go even higher by using point sprites instead of these geometry cones. But of course, it depends on your grid resolution, your particle count, your GPU, and the rest of the settings in your network. But direction is clear. This approach scales much better than a direct neighbor search. So, here's the trade-off. Neighbor pops gives you precise per particle information at the cost that grows with the particle count and the neighbor count. And the probe grid gives you low cost and fixed resolution view of the space. You lose some fine local detail, but you gain the system that stays fast at much higher particle count and gives you data you can reuse, filter, and sample from anywhere. Before I show you the full probe grid algorithm, let me show you the basic building block, reading 3D texture as a data. Here I have a very simple setup. A 3D pop with some noise inside it, and I'm using lookup texture pop to look inside this texture and to sample it directly. The texture is just a container of the values in space, and you can read from any position and use this value as a particle force or as a color or as anything else. And here's how I use this grid in this Boyd simulation. By the way, this is also a wonderful example of when feedback pop makes total sense. We need information from our previous frame to update this sensory grid, but we are not moving anything here, so feedback pop fits well and much better than the particle pop. For each probe's neighbor pop gathers some information about nearby particles, but this time it finds the neighbors between the particles and the probes, not between the particles and the other particles. So its GPU cost is less affected by the number of particles. Each probe gets two things: how many particles are nearby and their average velocity and direction. The particle count becomes raw density. The average velocity updates something I called trail velocity, a value stored in the grid that represents the recent local flow. Each probe also stores the maturity value. Think of it as a memory that becomes more stable over time if the particle flow stay consistent. If particles keep moving through this probe in a similar direction, frame after frame, this memory becomes stronger and more transformed, and the trail matures. But if the local motion is chaotic and particles move in different direction, the velocity cancels out the average, and result becomes close to zero, and the memory barely grows at all. Without fresh, consistent motion, the memory also slowly fades over time. So a probe is not just recording were the particles here, but instead it's asking, was there a constant and consistent direction of the movement here? And how confident am I about this direction? Now, this local information gets converted into 3D textures, one for the density and another one for the trail, using a pop to top node. And here's another nice thing you can do once you have a data in the grid. You can convert it into 3D texture and use a variety of top nodes to work with it. For example, I'll take this density texture and I run it through the slope top in the 3D mode. So this calculates the gradient, the direction in which density increases across the space. And now a particle sitting everywhere in this grid can find out the density is increasing this way, or decreasing. This data lives in a full 3D texture. This works for any location, the whole volume, not just the nearby surroundings. In the classical boids, you only care about the area right around each particle, but here I also give the particle a forward vision, but more on this a little bit later. The grid and sensors can provide the data from anywhere in the space, and it opens a lot of other uses. Now let's put it together. How does particle actually use all of this? Each particle samples the density texture and its own position. If density is below a chosen minimum, the particle steers along the density gradients toward this higher density. That's cohesion. If density is above the chosen maximum, it steers in opposite direction. That's the separation. Between those two values, neither force is active. And one important detail, this maximum density value should stay below the maximum neighbor count you set in the neighbor pop. If you set, say, 100 particles per probe, Then if you set U density max to 300, it doesn't make any sense. The system can never actually reach this value, so it will not distinguish between different crowded area properly. And the particle also samples the trail texture and compare its own velocity to the trail velocity that stores in this texture. A mature, strong trail pulls the particle, and young or weak trail only a little bit pulls at it. So we have replaced look at your neighbors with look at the memory stored in the grid. We still have the controls for the forces, for the turning, and for the speed, but the algorithm is very different now. Results still looks like flocking, but also could behave more like a trail following or Fusarium-like simulation. Depending on your settings, sometimes you can get something more like a flow field. And here is one more capability I want to highlight, because it shows something that direct neighbor pop search cannot do easily. Before finalizing direction, the particle preview where it would end up a few steps ahead at a cruise speed. Then it samples the density texture at that final position too. If that spot ahead is overcrowded, it adds the braking force against its predicted direction. So it's like an early response to congestion. The particle starts slowing down before it actually gets really crowded, while the other steering forces still have time to redirect this particle to somewhere else. And this works because the grid and this 3D texture actually lets us sample the density anywhere, not just nearby the particle itself. To be honest, it doesn't affect the result as much as I expected, but I still leave it here anyway. And finally, all of this cohesion, separation, trail following, and the forward braking combines into one desired heading that becomes a target velocity. The particle converts the difference between the target and its current velocity into acceleration. It limits how sharply that acceleration can change, then multiplies by mass, and it becomes the force that's sent into the particle pop. So this version also uses the full physical integration. It's just sensing the world in a completely different way. And here are the last thing I want to show you. It's another reason I like this approach so much. Once you have a spatial or sensors like this, you can store the other kind of data in it as well, because you have a lot of like unlimited time of pop attributes. I can use the exact same grid, the one that already tracks the particle density, to also calculate and store some lighting information using spherical harmonics and use it later in rendering. If you want to go deeper into this, I have a separate video series specifically about it. But here is my result. I could even feed this lighting data back into particle behavior algorithm and make particles photosensitive and react to the light. Leave me a comment if you're interested in this topic. So, probe grid converted to a 3D texture or not converted to a 3D texture is a good way to store and reuse spatial information. So, to summarize all the choices one more time. If you have a feedback loop, but not specifically for the particles, use a feedback pop. If you need it for the particles, but you want to control the position and velocity by yourself, use the particle pop, but turn off the time integration parameter. If you want to use different mass for different particles, drag, velocity, and other physical behavior handled for you, turn on the time integration. But be ready to redesign your algorithm around force and not around the direct control of a velocity and the position. And separately, you have another choice on the sensing side. If you need a precise per particle local information and your particle count stays reasonably low, neighbor pop works well. But if you want to scale to much larger particle counts and you are fine with trading some local precision for reusable, persistent spatial memory, a probe grid is worth learning. And of course, you can combine them. balancing the pros and the cons of each approach to fit your ideas and the particle system you are building. As I mentioned earlier, all the shader code from this video is open for everyone. The full project, including the prepared network and the rendering setup, is available for my Patreon paid subscribers. Both links are in the description. Also, right now I'm experimenting with different styles of tutorials, and this one is more focused on the theory and architecture and the reasoning behind the choices you can make. Let me know in the comments, do you enjoy this kind of approach, or you prefer more step-by-step making from scratch? And that's it. See you next time, and bye.